The last video we saw about the cosets of a subgroup in a big group, right? Now we want to talk about the cosets of a normal group. So first we want to interpret normal groups in a very particular way that will enable us to do some really nice things. So the way we define normal groups is basically that for a normal group of G, its conjugates will be the same thing as the group itself. So for all elements in G, the conjugate G and G inverse, or G inverse and G, whatever you prefer, that's just n, right? We can rewrite this equation as Gn equal to Ng. So this is the left coset and this is the right coset with the element G. So G and G inverse was defined as G small and G inverse for n in n. Right. And we know that this thing is just going to be the group n itself. What that means is that G and G inverse can be written as n sub 2 for some n in n2 in capital N, right? And this is going to happen for all n in n, and this happens, right? But we can rewrite this equation to say that okay, Gn is equal to n2g, right? There exists an n2 in capital N such that this happens for all n in n. And so essentially what you're saying is that G capital N, that is that's actually a subgroup, or I shouldn't say a subgroup, that's more like a subset of n2g, sorry, of capital Ng, right? Because it could be that it's like all mapped to the same n2 or something like that, right? So it's essentially just a subgroup, right? But then we can go the other way around as well, you know. So since Gn so since Gng inverse is equal to n2 for all capital G, sorry, for all small g, it's also going to be true for the inverse of any element small g, right? And so essentially what you also have is that for all n in n, you have G inverse n G equal to n2, right? There exists some n2 such that this happens in n, obviously, such that G inverse Ng is n2. So essentially Ng is equal to G1 n2. And so what we're saying is that capital Ng is now a subset of G times capital N. And so the only way this happens is that Ng is equal to Gn. So for a normal subgroup, you can rewrite this equation as this thing, and this is useful because now we can do some very funky stuff with this thing, right? So what we can essentially do is multiply two cosets of the normal subgroup. So let's take G1n and try to multiply it with G2n. So the way this multiplication works is pretty like straightforward. So for any two subgroups h and k, the way this thing happens, h times k, is just it's just hk for h in h, k in k. The same thing happens over here as well. G1n is some set, G2n is some set. The way these are multiplied is just, G1 n1 G2 n2. Yeah, I think that's the way to do it. For G1 n1 in capital N, G1 n, and then G2 n2 in G2 n. But then this thing can be written as just n1 in capital N and n2 in capital N. So essentially just n1 n2 in capital N, right? Yes. So notice that you can sort of, what was I going to say about this? Right, so you can rewrite this thing by noticing that you are essentially writing G1 uh, how do I even say this thing? I think this is a good way to be saying it. So essentially it's just G1 times this set of N1 G2 such that N1 is in capital N, and that times N2 such that N2 is in capital N, right? And so this thing is just essentially capital N itself, like don't worry too much, it's just this. But this is this is the coset, NG2, right? The right coset. Yeah, but what you can do now is actually rewrite this because of this fact. So it becomes G1 G2n, and that times n. So that's just G1 G2, and then n times n. What is that? It's just you know you basically like take all the elements from normal subgroup and multiply them with everything from the normal subgroup again. But clearly this other guy actually contains identity, right? So identity is a normal subgroup, and so capital N is a subset of n times n, but then obviously n times n can only have elements in capital N itself, so that's a subset of n. And this is due to the fact that capital N is a group, and we're just doing multiplication over here, like inside of the set notation. So essentially capital N times n is just n itself, and so we can just write it like that. I should write it like this actually. And so multiplying two cosets suddenly makes sense now, and this just becomes like, okay, G1n times G2n, that's just G1 G2 times n, right? Yeah. Okay, cool. So armed with this new fact that we can multiply cosets, let's try to multiply cosets in this very nice fashion. Let's try to just think about all the cosets of capital N in the group G, right? So we are thinking of this set Gn such that G is in G, right? We can notice some nice properties about this. That firstly there's closure, right? So for any G1n and G2n, you multiply them together, that just becomes G1 G2 times n, but then this thing is something from capital G, so that's another coset. And so there's closure. There's also inverse, right? You just have to like have a G1 inverse over there, and then obviously multiply that, you just get G1 inverse, that's identity times n, so that's just n itself. So inverses exist. There's the identity element, so G1n times n, that's just G1n, right? For any G1 in capital G. Yeah, so identity exists, there are inverses, there's closure, and obviously there's associativity, right? So like you just have Gn times, so G1n times G2n times G3n, right? If I had the bracket over here first, that would be something like G1 G2 capital N times G3n, which is just G1 G2 G3 capital N. But if I had the if I had the bracket on these two first, it would still be the same thing. We just get G1n times G2 G3 capital N, and that's G1 times G2 G3 capital N, which is the same thing as this. So there's also associativity, and so this multiplication, right? Yeah, that's a group operation over this set essentially, right? So let's call this set as or more like set armed with multiplication of sets in the way that we defined it, as the thing called G by N, right? Yeah. So this is called the quotient group of the quotient group of G and N, where N is a normal subgroup of capital G. So if I had to like rewrite this whole thing, then what I should be saying is that for any normal group of G, the quotient group is just defined as the set of all cosets in of the normal subgroup in G, armed with multiplication as the operation, right? Yeah, that's cool. So that's quotient group. Now let's use this and see if we can like do something with this. All right, let's like try an example first. Okay, so let's think about the permutations of three objects, right? But that's actually just going to be the S3 group, right? And it just so happens is actually the same thing as the D3 group, but never mind all that. So just think of the S3 group, right? It's the symmetry group on three elements. We have a normal subgroup which is called A3, and this is also called the alternating group. But essentially, um, so A3 is something where you only have the, what was I going to say? Yeah, you only have the rotations essentially, right? Yeah, it's like two transitions. So you only have the rotations. So it's actually more, it's slightly more it's a bigger definition than just that. But for this simpler example, A3 can just be thought of as this thing. It's just R squared. So S3 or D3 is actually the same thing as D3. That's this thing, right? R squared SR squared, right? Well, A3 is just this thing. And so now let's try to figure out what's the quotient of S3 with A3. So what's the coset of A3, right? What are the cosets? We know that the cosets of A3 completely cover the group S3, right? So there are only going to be two cosets essentially, because this is like three elements. We need three more elements, and that's going to be like covering it completely. And we know what that's going to be. So it's A3 and S times A3, right? Because S times E is like S and then SR and SR squared. So that covers everything. Yeah. So you can already notice that this is a group, because okay, you just have to verify it for yourself, like this multiplication makes sense, there's inverse and all that stuff. So SR is like its own inverse, A3 is its own inverse, this is the identity element and all that stuff. So yeah, this is a group, and this is essentially the quotient group. It's the S3 by A3 thing. In general, Sn over An is actually having just two elements. It's essentially I don't want to get into transpositions on that, but it's just two elements. That's what you need to know for now. All right, so that was cool, I think. Yeah, right. I think another way to sort of say this is more like, okay, this thing might be just better. So Tn upon Zn. I didn't say Zn. Zn feels bad. Cn is better. So it's a cyclic group on n elements that has size 2. That's actually an example that we can deal with right away. Yeah. Yep. So Dn upon Cn. So Dn is the dihedral group over some n gone, right? And Cn is just the rotations essentially. So that quotient is once again just it's just, well, it's a Cn and SCn, right? And this is a general thing, obviously. Now a nice property obviously is that the cardinality of this quotient thing, so G by n is precisely just the cardinality of G upon the cardinality of n. And here we're talking about finite groups. With infinite groups it gets weird, because like this thing doesn't make any sense. It's like infinity over infinity, what's even going on? But yeah, for finite groups it's just G by n, and you don't even have to need to have this as a group for this to be true. If you just define this G by n thing, or more like G by h thing, for any subgroup h, you can define it as just the set of cosets, In that case, yeah, so in that case, you can just say that the cardinality of G by H, which is also written as this thing, it's just the number of cosets essentially. That is just the cardinality of G upon cardinality of H by Lagrange's theorem. Come on, you know it, right? We just did this in the last video, and so this should be obvious by now. Okay, so yeah, I'll see you guys in the next video.